Değerli katılımcılar, ikinci davetli konuşmacımız Profesör Doktor Sayın Oktay Pashaev'i sunmak üzere Profesör Doktor Sayın Elgiz Bayram'ı sahneye davet ediyorum.
Teşekkür ederim. Evet Oktay Hocam, 5 dakika geç kaldı ama bu 5 dakikayı biz sizin değerli konuşmanızı dinlemek için size vereceğiz, tamam mı? Size başladığınız yerden 45 dakika, tamam mı? Evet, Oktay Hoca Moskova Devlet Üniversitesi'nin fizik fakültesini bitirmiş 1978 yılında. 1983 yılında dünyaca ünlü Bagalyubov laboratuvarında doktorasını yapmış ve 20 yıldan fazla, 21 yıl hatta Moskova etrafındaki ünlü Dubna Nükleer Araştırmalar Merkezi'nde çalışmış fizikçi olarak. Daha sonra 5 yıl Tayvan'da görevli olarak çalışmış. Tayvan Akademik Sinitse'de. 2000 yılından da arada bir yılda Türkiye'de çalışmış. 94-95 yılları arasında. 2000 yılında İzmir Yüksek Teknoloji Enstitüsü'nde araştırmacı profesör olarak görev almış ve halen de hocamız orada görevini sürdürüyor. Çok geniş bir yelpazede hocamız bilimsel çalışmalar yapıyor. 150'nin üzerinde çok iyi kaliteli dergilerde hocamızın makaleleri vardır. Özellikle de çok sayıda makaleleri integrallenebilir sistemler, kuantum teorisi, hidrodinamik ve uygulamalı matematik alanlarındadır. Hocamızın en son bir de söyleyeyim, H indeksi de 22'dir. Bunları ben bilgisayardan, internetten aldım. Hocamızı davet ediyoruz konuşmalarını yapmak üzere. Buyurun hocam.
Çok teşekkür ederim. Çok teşekkür ederim. İlk bu davet için çok teşekkür ederim. Ekim Hoca'ya. Uygulama matematik istiyorlar. Ben de uygulama matematik çalışan insanım. Şimdi benim konuşmam İngilizce olacak. Onun için ben 25 yıl İngilizce ders veririm. Ona göre bana Türkçe zor olacak vermek. Tamam. Let me start from the poster what you have. In poster we have seen numbers 1, 2, 5, which are Fibonacci numbers. Then in poster you have seen golden ratio. It is spiral of golden ratio, and we hear some music. We started this. I will connect all this together in the title of quantum calculus. So let me start from what is the Q calculus? Q calculus based on finite difference, but in the size rescaling. This is bir dakika bakın. Evet. So when you multiply, Q is parameter, which you multiply Q, Q square, Qn. So this is just one of the example, popular example. I will start very popular way, so I am using two principles. First principle, it is from Enrico Fermi. He told that when you are writing some article for the encyclopedia, first few sentences should understand everyone. After this, you can write what you like. Second, it is from Ludwig Fadeev, who frequently in his seminar, when he gives presentation, telling that this is reclam, because impossible to give all details. Okay, so this is, let us say, this is why I will start from some simple elementary example. This is bouncing ball, which is losing energy. This is why it is jumping up to distance, which is multiply h with multiple some parameter q, q square, qn, etc. But when you calculate full lengths become finite. Because q is less than 1, it is infinity in q calculus. Next example, it is from damped oscillator. Oscillator with damping amplitude. And if you look period of oscillation, then during the period of oscillation, you have this type of geometric progression in the amplitude. And this type of geometric progression, it's called Fermat partition. Why? Because a long time ago, famous mathematician Pierre Fermat which is known also from your title of your poster. In poster you have seen last Fermat theorem, a big Fermat theorem. And Fermat also discovered first integral, let us say, without taking integration. What he used, because when we teach calculus, usually we use equidistance partition, it is standard, right? But he was more clever. This is why he used partition by geometric progression. So he multiplied this by q, q is less than 1, this is why you have this set of areas. And then he calculated Riemann sum. This Riemann sum, you have infinity in q, and infinity in q everyone knows, right? It is infinite geometric progression. He gets this result. And area under the curve appear when you take limit q going to 1. So this is a known result if you take integral. As Fermat partition also can be related with analytic functions, because clear that if you calculate this type of area on Fermat partition, you can combine these q parameters as an analytic function because it's power series. So in this sense, any real analytic function is area on Fermat partition. So we can establish such type interesting relation. Next, Fermat partition and Jackson integral. Jackson integral, Jackson, main person who was in 19th century working on quantum calculus, and he discovered a quantum derivative and quantum integral and corresponding exponential function, Jackson exponential functions. But it happens that if coefficient an, it is just function of q power n, then area calculated this way, it is just definite Jackson integral. So Fermat did Jackson integral before Jackson around 200 years before. This is another analog of the Fermat partition, which is guitar fret. Guitar fret we use usually in Western music 12 intervals. This, according to this number, q is less than 1. This is interesting part because this is relation between q and h calculus. Q calculus, you play guitar when, right? Because you are using string, and Pythagoras rule that frequency of the string is proportional to the size of the string, inverse proportional. So then in big piano, you have strings here, which are using q calculus, but these are equidistant partitions. So this is why it is just mechanical relation, which mathematically we write as a logarithm transformation, okay, between these two calculuses. Okay, and then briefly about what is the quantum calculus. Quantum calculus term coming from Victor Katz in his book, which is very popular and very good book. But historically it started probably from Euler, Euler identity, then Gauss binomial introduced Fermat partition, I already mentioned it. And then this, it was worked some people like Jackson, Heine, Jacobi, Ramanujan, and others. And application in mathematics include combinatorics, number theory, modular forms. Non-commutative geometry, it is more recent when the quantum mechanics applied to the geometry. And it became rediscovered at the end of the 20th century by introducing the quantum integrable systems. It is so-called exactly soluble model with beta ansatz, spin models, quantum spectral transform. So this is analog of spectral transform, but when you have quantum operators instead of functions. And then Young-Baxter relations and quantum groups. After this, many papers appear at the end of 20th century, beginning 21st, Q-deformed physical theories. Everyone tried to do some Q deformation, KP solitons, non-NLS solitons, and others. But interesting problem still, I mean, I'm interested in, and I will talk about this. It is open problems like what is the real physical application of this Q? Because Euler, Gauss, Fermat, Ramanujan, they wrote a lot of very beautiful formulas, including this Q. But what is the physical model which can reproduce this type of behavior? So this is why I will try to answer partially some answer on this question. So outlines of my talk following. First, quantum calculus in classical hydrodynamics I will discuss. Then Q dispersive integrable nonlinear Schrödinger equations. quantum calculus of operators in quantum theory, golden quantum calculus, Fibonacci numbers, quantum coin flipping, and supersymmetric Fibonacci numbers. So first let me start from quantum calculus in classical hydrodynamics. I will start from the fascinating object which everyone knows, historical mirrors. Right? Mirror we use everywhere. Historically, most oldest mirror is a Neolithic site of Çatalhöyük, 6,000 years. It is in Ankara Museum. So mirror was used in physically in many applications. So this is, everyone knows parallel mirrors when you can create infinity because you have infinite images inside of parallel mirrors. This is another type of mirror. You have some picture which you cannot recognize what is this. If you put here cylindrical mirror, you can see the image because it is cylindrical mirror. In cylindrical mirror, image is deformed. This is why you cannot recognize it in the plane. Also, I should mention recently I found some paper about Mirat, it was mirror in old time, and mirror in Sufi, Abdurrauf of Sinikli. He wrote a paper in modern style paper, let us say book, in which he discussed humans according to Sufi and mirrors. In mirror, you know, if you have just one reflection, it is changing parity, left-right parity. If you have double, it is returning back. This is why he says that perfect person with God, it is when you have double or even number of reflections, odd when you have just changing your parity from left to right and others. Okay, so let me then, but mathematical theory of the mirrors started from William Thomson, Lord Kelvin, classical method of images he introduced. Idea is that you can replace boundary conditions by images of the given, let us, okay, if you have just image of person, so you have mirror. Mirror, it means that you have boundary for light reflecting, right? But instead of this, you can see yourself, right? This is your mirror image. And Maxwell, in his famous treatise on electricity magnetism, devoted 2 chapters. One is theory of electric images, another application in 2 dimension complex analysis. And another one is Poincaré lecture on the vortex theory, theory of turbulence. In the chapter 5, he discussed point vortex problem and method of images. And problem of hydrodynamic problem related with problem of images is first one cylinder problem, which was motion of 1 and 2 vortices when you have one cylinder, which was reformulated by Milne-Thomson as a one circle theorem. I will mention this soon. Then 2 cylinder problem, which is discussed by Poincaré. And when we started this problem to study with my colleague, August Yilmaz, that time I found that it can be related with Q calculus. This was very surprising. And then I formulated a generalization of this as a 2-circle theorem, then the wedge theorem and strip theorem. So briefly I will mention them. So let me start first. What is the relation between analytic functions and 2-dimensional stationary flow? This is standard part of the classical, let us say, complex analysis. If you have incompressible flow, you have divergence of velocity 0. This implies existence of function psi, which is called stream function. Second, if your flow is irrotational, rotor u is 0, then you have velocity potential according to this. But if you have now incompressible and irrotational flow, then this produces you Cauchy-Riemann equation. Cauchy-Riemann equation, as we know, conjugate functions, phi and psi, you can combine as a complex analytic function. So this is why every complex analytic function describes incompressible rotational flow and opposite. Every incompressible rotational flow is described by analytic function. So this is example when you have analytic function with logarithmic singularity, velocity, which is just complex derivative of the f, give you pole singularity. So we have then meaning of the pole singularities. And in principle, according to this, we can classify all singularities. Then when you teach Laurent series for the students, every term in Laurent series has meaning, because first term, when residues, it is exactly simple pole singularities, then you have multiple pole singularity expansion. So this way you have relation between physics and mathematics. Okay, but now we are going to the problem in bounded domain. Domain bounded by some curve. So then question is, we need to find analytic function which satisfy following condition. Imaginary part of f is 0, which means the stream function 0. So this is equivalent to conditions that you have normal velocity 0, you cannot cross boundary. Okay, and Milne-Thomson formulated so-called circle theorem. So if you have f of z, it is some flow in the plane. When you introduce boundary, it means that you should add here complex conjugate function, but at inverse point. This is inverse in the circle with radius r points. So then you get this potential which describe your boundary problem. So you don't need to solve it by power series and other stuff. So it is very powerful theorem, because for this you can substitute, for example, here, if you have point vortex, I wrote it as for velocity. This is your point vortex. Then you have image, which is located at, this is your point vortex, this is image located at inverse point. And one extra, which is coming because it's not fixed by boundary. Okay, but question become more complicated if you have two circles. In this case, you have double connected domain, and Riemann mapping theorem that is valid only for simple connected domain. So extension to multiple connected domain is not straightforward. Only what we know is that if you have double connected domain, you can conformally map annular domain which between two radiuses R1, R2 uniquely up to linear map that this is preserved. But this preserved ratio is exactly our Q number which will appear. Okay, so this is example, physical example. This is called Flettner rotor ship. So this is ship which is using two cylinders. These cylinders are rotating, and according to this rotor ship is moving. Okay, so according hydrodynamics, you have problem with two cylinders. If you intersect these two cylinders, then you have those two circles. So you need to solve problem with two circles. And for this, I formulated theorem. It was in 2012. Flow in annular domain we consider between two concentric circles. So it is consists from FQ. This is so if F is original flow in the plane, when you introduce two cylinders or two circles in annular domain, you have two functions. First function, it is infinite sum from minus to plus infinity, scaling z with q power n, when q is the ratio of two radiuses. Okay, so. And second one, it is this corresponds to images in even images in the one circle in another one. Another is odd images. So this is example of this type of. So instead of one problem in one annular domain, we have infinite set of images. Okay, and what is interesting, this function is Q-periodic function. It means that if you multiply, so you can choose any image as an original flow, and then you get again repeating the images because they're infinite. Okay, so this can be reformulated in terms of the Q derivative. This Q derivative, it is just this form, which is the difference between function and the with argument qz and z, and this is 0. Okay. So for velocity, which is complex derivative, it is so-called scale invariant function. So this is interesting point because scale invariant function in generally, if they satisfy such law. So if you rescale your argument, function is multiplied. So function preserves the form. This is important, but multiply with some coefficient q power d. D characterize level of your scale invariance. If you calculate Q derivative, quantum Q derivative, then this becomes a Q number, so you have Q difference equation. This is some type of scaling transformation in terms of Z, Q derivative Z, and this is Q number D. Then if we look solution of this equation, if it would be standard derivative, you will get just z power d. Since it is q derivative, instead of constant, now you have q periodic function. So this is called q periodic modulation to the usual solution. And most famous example of this, which everyone probably knows, it is Weierstrass-Mandelbrot function. It was proposed by Weierstrass in 19th century first, when you have summation from 0 to infinity of this function as function which is continuous but nowhere differentiable. Because it is convergent, but when you take derivative inside of cosinus q power n going to outside differentiation, then you have divergent series. This is why derivative is not divergent, not convergent. Okay, so then this function is satisfies the same equation, q difference equation, and it consists from this q different part, which is just q difference modification, q periodic modulation. Okay, and since you have this type of function with q periodicity, we can relate with complex variables z. We can relate it with elliptic functions. In book of Ahiyezer's famous book on complex analysis, you can introduce two numbers, omega and omega prime. One is real, one is imaginary. Q is defined in this form, and instead of this q periodicity, you can look logarithm z function in terms of logarithm. It is exactly this piano transformation which I showed. So this piano transformation from q periodicity produce you a standard periodicity in omega prime, but since we have also symmetry rotation in angle 2p around origin, we have second periodicity. Omega omega prime are different. This is why you have double periodic function, and what we know is that these functions related with Weierstrass functions, elliptic functions, but you need to fix singularity to see which function should be used in this case. Okay. Okay, so in problem which I am considering, so let us look, for example, simple vortex in annular domain. Then it is logarithm which I already discussed, but now you have this q-periodic extension, you have infinite sum which include, you see, all powers of Qn and images of Qn. According to this, we get also velocity, which is q self-similar function, which is with such q modification. So this is look like Mandelbrot function, which is example of the fractal. In this sense, this has become two-dimensional example of the fractal structure. This is analysis of pole singularities, and surprisingly, this pole you have infinite set of point singularities. Always to work with infinite series not convenient. This is why some mathematician introduced some function which first was elementary function and then special function. In this case, we can introduce so-called q logarithm function to count all these singularities. I think, yes, it is. First, let me check about the geometry of the problem. I have, you see, this is annular domain. I have that in this annular domain just one vortex. This one vortex produces green vortices in two circles, but then this green vortex you should reflect in the big circle. You get this one, the red one, and red one in this case, and then you get Fermat partition lattice in one dimension. One is for even, another for odd vortices. Poincaré was working with the series and told about convergence of series, but not with such type of theorems and functions, because it was quite short. It was 3 pages, I think, in his lectures. So q logarithm function, analog of the standard logarithm, define it in such way, but instead of n, you have q number n, and then this is what is important, fundamental property. We can expand nq in terms of q, and then if we recombine series, then we can rewrite it in this form. So it happens that singularities of this function appear at, as a simple poles at Fermat partition or at a geometric series. And what is interesting, this logarithm function related with derivative of q exponential, Jackson q exponential function. Okay, so according to this, we can then introduce elliptic functions, Jacobi theta function in this infinite product form, and the problem can be reformulated in terms of elliptic function. And some people work in elliptic function approach because it's conformal mapping, but in this case, geometry is changing because elliptic functions, you have not Q symmetry, you destroy symmetry.